So hi and Assalamualaikum. My name is Nur Safia binti Muhammad Muhyiddin. My matrix number is 222010883. So today I'll be explaining about a question regarding my topic, which is thermal equilibrium electron and hole concentration. So my question today is, consider a germanium semiconductor at T at temperature equals to 300K. So in which electron density Nd is given by value Nd 8 times 10 power 17 and Na 2 times 10 power 16. So intrinsic carrier concentration for germanium is 2.4 times 10 power 30. So the question is 1, thermal equilibrium electron and hole concentration, and it wants us to recommend either the material is N-type or P-type germanium. So just over here I'm just writing over again for Na value, Nd, and also Ni. Then I'll be comparing the value for Nd and Na. So if for cases like Nd more than Na, so the recommended value, the recommended semiconductor material would be N-type germanium semiconductor material. Excuse me. Okay, so for the next step, I would be searching for the thermal equilibrium for electron concentration. So first, the Ni is intrinsic carrier concentration for germanium, which we got from the questions. So firstly, for thermal equilibrium electron concentration, NO, okay, so we'll be using this formula. This is like a fixed formula for thermal equilibrium electron concentration. So which is Nd minus Na over 2 plus Nd minus Na over 2 square plus Ni square and square root the whole thing. So this is the highlight of the show, no? It's highlight for the future courses. Okay, so NO is equal to 8 times 10 power of 17, that is the Nd, and then minus 2 times 10 power of 16 over 2 plus with the same thing and power of 2 and square root 8, and then 2.4 times 10 power of 13 is the Ni, the intrinsic concentration, and square root the whole thing. So the answer for electron concentration is 7.8 times 10 power of 17 cm. Okay, so for the second one, I'll be searching for the thermal equilibrium for hole concentration, PO, for germanium. So for this one, we'll be using mass action law, which is NOPO is equals to Ni square. So PO is equals to Ni square over NO, which is hole concentration is equals to intrinsic carrier concentration over electron concentration. So the answer for hole concentration would be 7.3846 times 10 power of 8 cm negative 3. So that is the formula for PO, and this is just, decorating. Okay, so I think that is all from me. You can skip this part and go to the next part. Okay, bye.
And proceed to next question, which is consider a silicon semiconductor at T 300K in which electron density Nd 4 times 10 power of 15 centimeter minus cube and hole density Na 1 times 10 power of 15 centimeter minus cube. The intrinsic carrier concentration is assumed to be Ni equal to 1.5 times 10 power of 10 centimeter negative cube. Determine the thermal equilibrium, electron and hole concentration. Recommend either the material is N or P type silicon. Okay, proceed to the solution. We have here is electron density, which is Nd, and hole density, which is Na. So in this question, Nd is greater than Na, which is we can assume in this question is N-type silicon. So firstly, to find the electron concentration, which is N0, we can use the formula N0 equal to Nd minus Na divided by 2, and is all plus with square root of Nd minus Na square divided by 2 and plus Ni square, which is an intrinsic carrier concentration square. Then we apply the value given, which is Nd is 4 times 10 power of 50 minus Na 1 times 10 power of 50 divided by 2. And we also apply the value for the square root. Nd minus Na is divided by 2 plus intrinsic carrier concentration square. So the answer for the electron concentration A0 for this question is 3 times 10 power of 50. Next, to find the hole concentration, we use formula A0 times P0 equal to Ni square, which is intrinsic carrier concentration. So for this question, we must find P0 equation. So we use algebra method to find P0 equation, and here we get P0 equal to Ni square divided by A0. We use calculator to calculate the hole concentration. So which is we got 75 times 10.
Good day everyone, my name is Darshini Subramani and my matrix number is 222010820. So the topic given for us is thermal equilibrium, electron and hole concentration for intrinsic semiconductor from chapter 3. So the question for today is determine the thermal equilibrium, electron and hole concentration in gallium arsenide at T equals to 300 Kelvin. If the Fermi energy level is 0.30 eV above valence band energy. The value of Eg is 1.42 eV. In this question, the value of Fermi energy level and also the value of Eg is given. To solve this question, first we have to find the Ec minus Ef. To find this value, we have to minus the value of Eg with the Fermi energy level. So the answer will be 1.12 eV. For the NC, or in the other word, the value of effective density of state function in the conduction band is 4.0 times 10 to the power of 17. The value of NV is 7.0 times 10 to the power of 18. To find the electron concentration, first we have to fill up the following equation. For this, to find the electron concentration, 4.7 times 10 to the power of 17 exponential times with negative 1.12 divided with 0.0259. So the final answer for electron concentration is 77.95 times 10 to the power of negative 70. For the hole concentration, the step is same as the electron concentration, but there's slightly difference with the formula. For the NC, we have to, for the electron concentration, we will use NC. For the hole concentration, we have to change the NC to NV. Apart from that, we have to change the EC minus EV with EF minus EV. To find hole concentration, we have to substitute the NV 7.0 times 10 to the power of 18 exponential times with negative 0.3 divided with 0.0259. So the answer for the final answer for the hole concentration is 6.526 times 10 to the power of 30. So this is the final answer for the following question. Thank you very much.
Assalamualaikum and hi. My name is Muhammad Aman Rashmi Roslan. My metric number is 222010849. Today I will talk about intrinsic semiconductor. My question is determine the thermal equilibrium and Hall concentration in germanium at T equal to 300 K if the Fermi energy level is 0.3 above. The value of Eg is 1.42. Okay, first, if we get this question, first step we must know where is the Eg, where is the value of Eg, the value of band energy, and we must find value of Nc, Nv, and Kt at the appendix. So for this question, for germanium, Nc equal to 1.04 times 10 power of 19 cm square, and Nv equal to 6.0 times 10 power of 18 cm square, while Kt is equal to 0.0259. So first we must find Ec minus Ef equal to Eg minus Ef minus Ev. So the value is 1.42 minus 0.3. The value of Ef minus Ev equal to 0.3. So we can get the answer 1.12 Ev. So the question one electron concentration. So for the formula we can get at the appendix, and not equal to Nc Hp minus Ec minus Ep over Kt. So we just masukkan nilai dalam formula tu. Kita punya jawapan untuk electron concentration tu akan dapat 1.7428 cm padu. Sama juga dengan Hall concentration, kita akan ambil formula daripada appendix. Formula dia P not equal to Nv Exp times minus Ef minus Ev over Kt. So just masukkan nilai dalam formula, kita akan dapat 5.5939 darab 10 / 13 cm padu. For this question itu sahaja. So just kena tahu formula dan cara masukkan nilai dalam formula. That's all from me. Thank you. Assalamualaikum warahmatullahi wabarakatuh and good evening. My name is Haikal bin Samsudin and my matrix number is 222010817. Today I will present about this question, which is the question is consider a silicon semiconductor at T equal to 300 K in which electron density Nd and hole density Na is given in the following condition below. The intrinsic carrier concentration is assumed to be Ni equal to 1.5 times 10 power of 1.5 times 10 power of 10. Determine the thermal equilibrium, electron and hole concentration. Recommend either the material is N-type or P-type silicon. First, we know that Nd equal to 8 times 10 power of 14 and Na equal to 5 times 10 power of 15. So, for Na bigger than Nd, recommended P-type silicon semiconductor. So, from appendix, we can option value for intrinsic carrier concentration Ni for silicon is 1.5 times 10 power of 10. For thermal equilibrium hole concentration P naught equal to Na minus Nd over 2 plus square root Na minus Nd over 2 power of 2 plus Ni square. So, P naught equal to 5 times 10 power of 15 minus 8 times 10 power of 14 over 2 plus square root 5 times 10 power of 15 minus 8 times 10 power of 14 over 2 power of 2 plus 1.5 times 10 power of 2. So we get the answer, which is P naught equal to 4.2 times 10 power of 15. For thermal equilibrium electron concentration N naught, by using mass action law, NO minus P naught, N naught minus P naught equal to Ni square. So N naught equal to Ni square over P naught. So we get N naught equal to 1.5 times 10 power of 2 darab over 4.2 times 10 power of 15. So we get the answer for N naught equal to 5.357 times 10 power of 4. I think that's all from me. Thank you.